Buenos días. Bueno, estamos aquí reunidos para la defensa de la tesis presentada por Beatriz Arregui García, que ha sido dirigida por el doctor Sandro Meloni y que se ha realizado en este instituto, en el IFISC. La tesis se titula A Network Science Approach to Human Interaction Across Physical and Digital Spaces. La doctoranda tiene un tiempo de aproximadamente, es aconsejable, unos 45 minutos, no pasa nada y se alarga un poquito, y el tribunal posteriormente debatirá alrededor de 1 hora sobre los temas que considere oportunos. Antes de que comience la presentación, voy a presentar a los miembros de la mesa que me acompañan, miembros del tribunal. El doctor Gerardo Íñiguez, de Tampere University, de Finlandia. El doctor Javier Borge, de la Universitat Oberta de Cataluña. Y yo misma, Rosa María Benito, de la Universidad Politécnica de Madrid. Cuando quiera, pues comenzar. Como se trata de una tesis de mención internacional, entiendo que la presentación, no sé la normativa de cada universidad, si la tienes que hacer totalmente en inglés o tiene que ser mixta en la universidad.
It will be in English, I think.
Okay, so you can.
Well, yeah, it will be in English. Thank you so much, Rosa, for the presentation. And so here I will present my work with a network science approach to study human interactions, both across physical and digital spaces. And okay, sorry. And so I would like to start by acknowledging the richness of human interactions and how they can rise complex human or complex collective behavior. From the very classic example of the Karate Club network to more recent events like the GameStop short squeeze in 2021 that took place in an online platform, we see how even in very small systems such as the Karate Club, already structural patterns or coordination, like in this case, can generate some emergent complexity from how individuals interact. And this could seem just as anecdotal examples, but actually they are a hint of how human interactions are at the core, and they can shape more important and actually modern societal challenges. One of these important challenges that we face as a society nowadays is public health. In the last 2 decades, we have lived in worldwide emergent outbreaks of diseases such as the MERS in the Middle East, SARS, COVID-19, Ebola, the more recent monkeypox, that actually they have caused a lot of struggle and worldwide pandemic, some of them. And they rely heavily on human interactions, like physical contacts here. In the case of epidemics, for instance, they play a crucial role. Similarly, to the spreading of diseases, information and beliefs, they spread also through interactions, usually in this case in online spaces, in the case of communication. And it's not only about the content that is generated, but how this is spread, that communication on social media plays a role in our society. They can affect elections and democratic processes, also cause polarization in society. And even we could close the loop and say that communication about public health, for example, in the case of infodemics, can change the behavior of how we face outbreaks in pandemics with our behavior as a society. These are just some of challenges that we face as nowadays, and they motivate the use of, for instance, network science, and they motivate the study, modeling, analysis of human interactions to gain a better understanding in order to face and tackle real problems. In this thesis, we have tackled both interactions in physical and online spaces. In the first part, we focus on face-to-face interactions that, as we mentioned before, they play a crucial role in the spreading of diseases. We have adopted a methodological framework to study temporal networks, also account for group interactions, and with this build surrogate or artificial networks that will help to model diseases across different contexts. On the second part, we focus on digital interactions, in this case on Mastodon, which is a social network. And here we have studied the moderation process in this platform by studying the dynamics of the network and also the propagation of information in this network. So with no further ado, I will start with the first part on physical interactions. So as I mentioned before, diseases in a population do not spread homogeneously, but they propagate through patterns of interactions. And these contacts between people, these interactions, are not static. They are heavily dynamic and time-dependent. And considering this dynamics of the contacts is really important, since even in the same set of contacts, if you, for instance, reorder them, you will have different outcomes in an epidemic spreading. So the static framework is already, not enough to study physical contacts and their consequences in a disease spreading. Besides, usually individuals do not, they interact in groups. There are empirical evidence of how actually individuals form these gatherings where they, that you can even see that they dissolve in time and they reappear again, forming these stable social cores. And accounting for this group interaction is important. And also in the last years, we have seen an amount and growing amount of literature that start to include this group structure and revealing how considering it will also change the outcome of different dynamics from percolation to synchronization and also spreading. Okay, so how do we study physical contact? Actually, gathering data on physical contacts is not easy, it's very costly, and this makes that usually the available datasets are very short in time and there are very few, and there is a lot of scarcity across different contexts. So one alternative that we can do to study spreadings in different environments is to generate these contacts artificially, generating these surrogate temporal networks that are networks that want to really mimic the patterns in the observed data. For that, what the approach that we usually do in literature is to split and go and focus on the microscopic structure of the data and study these motifs or little or microscopic structures that form the interaction networks. We have seen that it's important to take into account the temporal perspective of these microstructures, and it's not easy to collect and to define this, to split these large networks into motifs. It's even more difficult to account for the temporal interaction, and there is practically no works where they also account for the group structure. So what we wanted to propose is to generate surrogate temporal networks by looking at their motifs, where we take into account also these group interactions, at least going beyond the dyadic interactions to triangles to account for triads. First, we want to see if these triads play a role in the macroscopic network. And if they do, let's try to aggregating them in the process of generating the synthetic networks. So for that, first, what we do is to mine these motifs. And for that, if we have a very large network, imagine we have this temporal network with a lot of temporal snapshots, and we will go and divide it in sets of 3 temporal windows. Once we have this set of 3 temporal windows, we will focus at a time in every of the nodes that is present in the network, and we will focus on the node that is the designated ego. We will take this egocentric perspective, and we will look at their neighbors and also on how their neighbors are connected among them. So in this way, we go beyond the dyadic perspective, and we also include how the neighbors interact among them. Okay, if we have a very large network already, mining these motifs is, is computationally heavy, but now we need a way to quantify them. So we can work easily with this and describe the network in an efficient way. For that, what we are going to do is to convert these little structures into a binary string. So we will go over every dyadic interaction first, and we will assign a 1 or a 0 every time step if there is a connection with the ego node or not. And we do that for every neighbor, and in this way we encode the first order interactions. Then we sort them lexicographically, and we will go over all the possible couples between the neighbors and the ego node, looking if there is an existing hyperedge, an existing triad interaction or not, and we encode them in the same way, with a 0 if they do not exist, or with a 1 if they are present. And this forms our signature. By merging them, we have this final binary key that we call the hyperegocentric temporal neighborhood signature, and which encodes every structure, every neighborhood that has this way univocally. And so every time that in the network we will encounter this, we already have a way of naming it. And we can apply this methodology to the large network. We encode, and we will describe statistically based on their motifs by looking at the frequency of all these signatures. And we compare the data sets with a null model, extracting actually the statistically significant signatures into the motifs. We have applied this methodology to study proximity contact data. Actually, most of the data sets are face-to-face interaction data. So this means that they are collected by putting in the chest of individuals a radio frequency sensor. And every time two people are face-to-face, there is a signal between the sensors. So an interaction is recorded between the 2 individuals every 20 seconds. And we have this information for different settings, such as a conference, a hospital, different schools and offices. Besides, we have also data on a university, but this one was collected via a Bluetooth technology, which actually records interaction to a much longer radio. What we do is to apply this methodology to encode this data set that we have, And we compare them, we compare their motifs abundances with a cosine distance, obtaining this distance matrix based on the motifs that we have encountered. And of course, what we see is that the most similar ones are those that have been collected in a similar setting. In this case, for example, in 2 office spaces, and this in high school. And also we can discriminate by technology. I mean, the most different one is the one collected in the university, since, as we said, the Bluetooth technology at the end will register much more contacts than in a face-to-face basis. And since we were interested in the role of the second order interactions, we decided to divide and see the differences between considering only the dyadic ones and the second order ones. And adding the second order interaction is what is going to help us to actually better differentiate, when we look at the whole neighborhood, the different data sets among them, since it includes much more variability in how the people interact with the other people and their neighbors across the different settings. And we can use this methodology not to only describe the whole data set, the whole temporal network, but to describe at a zoom level. So every node, we can also characterize them with these frequencies of neighborhoods. In this case, we did this for the hospital, since we have further information on the role of every node. The nodes can be patients or nurses or medical staff or administrative staff. In this figure, we see this multidimensional scaling where every node in the map is placed based only also in the distance between their motif distributions. The farther they are, it means that they are more different, and the closer they are, it means that they are much more similar. And again, we can see if we the fact of introducing the second order in the interaction in the whole description will help us to have more information that only accounting for the dyadic interactions. In this case, we can see here, like patients are the more are the ones showing the most similar behavior. With a less variety of interactions, while the nurses are the ones that are more different from the other groups, and also among them showing that they have a more different activity. So with this, what we have is just a statistical description to characterize large networks, focusing on their motifs, accounting for the temporal structure, and also going beyond the pairwise interactions. And actually, accounting for these second order interactions will help us to differentiate where the interactions take place depending on the context. So if they seem to play a role, why not try to introduce them in this generation of synthetic networks in these artificial networks, and see if actually we can generate more realistic ones. And I will explain very briefly the algorithm. Imagine that we have a hypergraph seed of 2 temporal windows. This, I mean, in the real networks are much more nodes. Here there is only 3. But for this hypergraph seed, we will sample for every node in the most probable continuation of their neighborhood. So we sample from the neighborhood distribution, which is going to be for every node the next step. And for this, we have a proposal for every node. And what we do is try to minimize the conflicts between the different neighborhoods that are proposed. And by minimizing this frustration between nodes, we will validate the new layer of the hypergraph, generating this new temporal snapshot, and we will repeat this process by taking these 2 last as the seed. And in this way, we can generate as many temporal windows as we want. Here there is some results of comparing the data with our generated synthetic network. In green, it will be the network where we consider the triads. of the interactions, while the orange one is just the dyadic version. And actually what we see is that including these triads will reproduce much better the data. For instance, the classic method, like just considering the dyadic interactions, will produce an overestimation of 2-node interactions, while it will barely capture any triad interactions as we can see in the data. If we measure further metrics in our results, this can be also, I mean, we see this effect of not producing the 3-node interactions, since even with the classic method, for example, the degree, it is more or less well captured. The clustering and also the assortativity and their interaction were not well reproduced, while introducing this second order effect captures really well the observed data. Okay. Beyond these more classic metrics, since we have now real hypergraphs, I mean, what we are generating are temporal hypergraphs, we have further checked these similarity measures that are specifically for accounting these higher order structures. We have the HyperNet Simile that looks at the local neighborhood of the nodes in the network, and we have the HyperH ported divergence that looks at the paths in the hypergraph, so giving a more global interaction structure. And first, what we saw is, I mean, what we measured, it's we compared data and model temporal layer individually. And here we see the average of these similarity metrics. And again, we see much better results by including the second order interactions perspective, since they are much more similar to the data across different settings. And this is again a comparison between data and model. This time what we did is to aggregate temporally the hypergraph. So we are just comparing the aggregated snapshot of the whole hypergraph. And here we can see well the effect of the second interactions, mostly when we compute this HyperH ported divergence that looks more at the global structure and not at the node level. So we have very optimistic results with this methodology by including the second order interactions. In showing, I mean, since our results show that our model reproduced very well the data, but still I would like to mention some limitations that we face. First of all, is about data collection, and this is, I mean, this is a general problem in the field, in the sense that the data is collected intrinsically pairwise, since the sensors will only detect interactions between two people at a time. So what we do in, I mean, what every work in this field, what we usually do is that we aggregate this from these 20 seconds to at least 1 to minute temporal windows, inferring that if A has interacted with B, B with C, and C with A, it's a triadic interaction. But of course, I mean, have a better understanding of the real data of how people are interacting in the group would lead us to then understand better the mechanisms and improve the models. And again, this also have then consequences maybe in the modeling of very large groups, like super events, that, for instance, our model is a bit limited when we have to reproduce peaks of interaction from more than 100 nodes. And in also adding larger memory to the process. In our case, our model is thought to have a short memory from 2 to 5, 6 temporal windows, but adding some larger memory mechanism would be an advantage for representing the real data. So this concludes the first part in physical interactions. And we will jump now into the digital space. A key motivation for the first part was the scarcity of real data and of real face-to-face contacts, and how could we generate real networks for that, artificial networks for that. In the case of digital space, I mean, it's not that we can access every data in the world because of privacy issues, but everything leaves a trace. I mean, when you buy something online, there is a trace. When you chat with someone online, there is a trace. When you access a website. So the data is much more abundant. This changes a bit our questions and the modeling and the tools we use to tackle these social systems online. Many of the interactions in these in digital environments in terms of social activity come from online social networks. Here there are many platforms that, I mean, there are a great diversity of platforms, but usually they limit how you can express, how hard you can interact with other people in just a few actions. You can express friendship through, I mean, maybe a friendship relationship or maybe a following relationship. You can express support maybe by liking or reposting something from another person, or even in the contrary, disliking something. And in the last years, social networks, the more mainstream ones, maybe like Facebook or Twitter, that at the end they are private companies. They have, I mean, there has been a rising concern about how they manage our interactions, our data, our privacy, since and also the moderation control in these social spaces. So that's why due to these rising concerns about the regulations on the more mainstream social platforms, there has been an increasing popularity of what we call decentralized online social networks. Here I have the example of the Fediverse. The Fediverse is a network of interconnected servers that communicate through an activity path protocol. In terms of technology, what this means is actually it works like an email. I mean, you don't have to have the same email provider to communicate with someone, to exchange messages. And this is more or less the same, the same mechanism. Within this Fediverse, we find Mastodon. Mastodon is a microblogging platform, just as Twitter. And sorry. Okay. And so in Mastodon works again upon an interdependent network of servers that are called instances. Here it would be an example of an instance that you can join. This gives users much more control upon how the user data is managed, privacy issues, because every administrator will regulate their own policies, and if you don't like any server in place, you can create your own and connect it to the network. As a user, you can, if you don't want to create your own server, or if you want, you can create your account into one of these instances. You can follow people that have their accounts also in these instances, or connect, follow, exchange messages with other people in the whole network. And what Mastodon offers in terms of moderation control is that administrator servers can block other instances. They can ban them. And so this will make that if one instance blocks another one, users in these ones will not longer see the content coming from the instance that has been banned. We have studied data on this social network. We had data on more than 25,000 instances, but and in their following relationships. But we were interested at looking really at the moderation process, and so we reduced our dataset to more than 5,000 instances, and we had information for them in their follows and also in their daily blocks. So we have analyzed for a whole year how these daily instances are being blocked or are enforcing the moderation from 2023 to 2024. So first, we were interested in studying the dynamics of this network, that we have sign edges and temporal activity. And so we looked at the possible structures of between couples of nodes. And we wanted to see how these dyadic edges were changing over time. So for instance, two instances that are not connected, maybe one blocks the other one, and studying all the different configurations and how they change in time. So we have the abundance of these 9 different configurations between instances, and also the transition matrix for every day. And when looking at all these transition matrix daily, they seem very constant. So we want to look if they were actually stationary, fulfilling this condition. And what we saw by looking at this stationary condition day by day is that not always it was fulfilled. But when aggregating this in time, so averaging over the whole year, the theoretical abundance and the observed one was in agreement. We checked this also for the change on the degree distribution of the blocks. So if one node was blocking one day 4 instances and the next one was blocking 2 more, how this changes. And we looked at it also daily and at aggregated over the year, and daily the theoretical and observed abundances were not matching, but looking at a year scale, they were. So it was interesting to see how we were passing from this to this. At which scale, temporal scale, this stationary process was emerging. So we measured we started by aggregating 1 day, 2 days, 3 days, and we measured the difference in the distribution, theoretical and observed, in this with this temporal aggregation. And actually, for more than 20 days, this was already reached. And this helps also for the condition for the detailed balance condition, not for daily observations, but when we look already for 30 days, so for a month scale, there was a very good agreement between the observed and the theoretical expectations. So, and this is, this was unexpected in the sense that the administrators are entering and exiting the network. We don't have the same moderators or the same instances throughout the year. There are instances that maybe are blocking during the first months, and then they disappear from the system. And new actors that are entering the system, but actually, by looking at the system with a month aggregation, we see signs of stationarity and equilibrium. So we were then interested in seeing how the propagation was transmitted in this moderation context. Because actually, by looking at the network, they barely overlap the instances that are enforcing the moderation, that are blocking, and the ones that are receiving the blocks. So they are two separate groups. So we define these two groups, the moderators that actually are a minority, are around 500 instances, while the rest, the majority, are the instances being banned. And we wanted to study the paths of propagation of pieces of information within the two groups and between them. So for that, we took this hybrid contagion approach, where, for instance, for example, this instance that belongs to the majority, if it wants to be informed, it can be informed from another instance in the majority with a simple SIR model and a probability beta. While if the piece of information is coming from the other group, so from the minority, we model this as a threshold model with a threshold parameter T. So it needs to have more infected neighbors or informed neighbors larger than T to get the information. And we studied the patterns of the 4 different patterns of propagation. And here we can see, we observe the final attack rate. It's the final fraction of infected or of informed instances. And what we see is regarding the self-spreading is that the minority shows a much higher connectivity. Many more instances will get informed from the same group than in the majority. While for the cross spreading, so how the information propagates across the groups, what we see is that actually from the passing the information from the moderators to the majority, so to the banned instances, is much more resilient under the changes in the parameter models. Based on these patterns of propagation and the final fraction of infected instances, we can define this information transmission bias. Here we would have just the average information transmitted. So, I mean, logically, when T is higher and beta is lower, less information passes through the network. And then we can have this emissivity bias and receptivity bias that by how they are defined, basically they say us that when they are positive, the majority is being much more efficient at emitting or receiving the information. In this case, we don't see a clear bias for the receptivity since it's near zero. But all the parameter space shows negative values for the emissivity bias, which gives us a hint that actually the moderators are the ones being more effective on passing the messages. And we have at last the echo chamber bias, which again, with values close to 1, it means that there is an echo chamber effect, while values near to -1, it would be a sign of an anti-echo chamber effect. That means that actually the information is flowing just between groups. In this case, we see a large range of values in being positive. Actually, we would say that all here, this is an echo chamber effect, which when we talk about information transmission in social networks, this is usually used to describe systems that are polarized. But in this case, what we want to stress is that those instances that are in the majority are being flagged already by spam hate speech, racism, and many other reasons. And what we see actually in the moderation context is that without a single authority dictating what the moderation policies, already a network and a collection of independent servers gets to stop the malicious content, the malicious sources out of the network. So here concludes also the digital part, and I just would like to wrap up by summarizing what we have done across this, along this thesis. We have tackled both physical and digital systems, and we have mainly focused on local structures and also stressing their temporal activity of human interactions in different contexts and how they shape broader patterns and can affect the behavior and organization of the different systems. In the first part, for the physical contacts, we had a more methodological approach, studying how second-order interactions, how triadic interactions in groups will help us to generate artificial networks that are very useful then to study diseases spread and epidemic spreading across different contexts where the data collection is difficult. But also we would like to stress that data collection in this context, it's going to be one of the challenges in this field, in the sense that right now it's not well prepared to account and understand these group mechanisms. So it's one of the challenges for the future to design a good collection of these human interactions to better understand them. In the second part, we have moved to the digital interactions in a social network. And here we have mainly studied a moderation process in an emergent online social network that right now is, in the last years, we have seen that this is a social issue that we are facing. Many people have been migrating from mainstream platforms to new alternatives. And there is still a lot of studying and understanding to do in a moderation process in these new networks that are more unknown. And this is it. Thank you so much for your attention. And that's it.
Gracias. Thank you very much. And now is the time of questions. Tiene la palabra en primer lugar el doctor Gerardo.
¿Quieres un?
Perdón, sorry.
Yo me quedo.